So there is no standard model. So I have a standard model t-shirt, keeping you in mind. No, no, wait. Not now. Because the paper is not out. You can record it. I'll hopefully out next week, and then you can.
Fine. Okay.
Yeah. Yeah.
You're doing it next year.
No, no, no. This is a group logo. If we have money, we can do it again. That the money is different. Yeah.
Okay, welcome everyone. We're very happy to have Arnab Rudra today with us, who's going to tell us about tree-level scattering of bosonic high-spin particles.
Okay, thank you. Yeah, thanks for the invitation and giving me this opportunity to talk about our work, which is yet to appear. So this is a work with Akash, who is a PhD student, Manav, who did MS thesis at ICTS Bhopal. He's now in Cambridge, and Rahul, who is in the audience. Hopefully, it will be out next week or something. So let me begin by asking the broader question that we are trying to understand. The broader question that I'm trying to understand is to find rules for perturbative quantum field theory involving massive high-spin particles. Okay, so I'll try to make this phrase a bit more precise as I go along, but that's basically the kind of question I'm looking at in last 3-4 years. And what we will be focusing in this talk is a much limited set of questions. The question that we'll focus in this talk is to find a tree-level scattering amplitude for two massless, either photon or graviton, and two massive high-spin particles. Tree-level kind of thing we do in QFT1. So as I said, there was a phrase called higher spin. So let's start from the thing that what do I mean by higher spin? So I will, yes.
Why massless scalars and two massive high-spin particles?
Yes, that is, I'll talk about it also. I'll also talk about it. Basically for photon or graviton, there is extra thing like gauge invariance, which gives more tools to constrain things. But so first step is to do that and then do these things. Yeah. So, okay. So we will restrict ourselves to flat space where the symmetry group is translation, rotation, and boost. And altogether, this is called the Poincare group. And as you know that the quantum particles are unitary irreducible representation of the Poincare group. And for purpose of this talk, I will do it in any number of space-time dimension. So where again the quantum particles are uniquely specified by mass and spin. So in 3+1 spin is a single quantity, but in higher dimension, spin is usually a set of real numbers. So what do I mean by that? Let me be more precise. So in n+1 dimension, the quantum particles can be characterized by the SON representation. So that basically means that quantum particle corresponds to some sort of young tableaus. Okay. So in this talk, we will only consider quantum particles which correspond to completely symmetric and traceless Young tableaus. Not because other things are not interesting, they are very interesting, but this is the simplest thing to do. So in the context of string theory, these are the states which belong to the first rigid trajectory in string spectrum. Okay. So, so what do I mean by higher spin particle? By higher spin particle, I mean any particle with spin more than 2. That will be the phrase I will be using. And in this talk, I will restrict myself to only bosonic particles. And in 1960s, mostly followed from Weinberg's work, that one can show that the high spin particles cannot be massless. There is no interacting theory of massless high spin particle in flat space. So that means we will necessarily be restricting ourselves to massive high spin particles. For symmetric representation generally, but in higher dimension, you can also in principle have mixed symmetric massless particles. To best of my knowledge, that is still not very, nobody has cleaned up that part. That is completely antisymmetric. But what about, let's say, mixed symmetric? Yeah. Yes. So in 3+1, black holes are also characterized by the same three quantities, mass, charge, and spin, as quantum particles. And I just stopped. I mean, this is just a question that whether this is a coincidence or someone can make more sense of this coincidence. And especially because in last few years, there has been few papers trying to do black hole scattering using these high spin particles. Okay. So with that context, let me be a bit more precise about high spin particles. So I will, the corresponding polarizations is something like a rank S tensor for spin S, which is completely symmetric. It should be transverse. So given the momenta, it should be transverse to the momenta and it should be traceless. So those are the conditions that is the restriction on the polarization. And in 3+1, they have 2s+1 independent polarization. You can show that in general that counting is possible, but it's more. So for the purpose of this talk, I will write this polarization as a product of vectors, which I call zetas. And that means this condition basically translates to that zeta is a null and k dot zeta is 0. The main reason to write it in this way is basically that big expressions like this, where let's say the polarization is contracting with some vectors, then that can be very quickly written as a very shorthand notation. It's basically for compactifying all the expressions. I will basically go back and forth. I will not use this, but I will use.
But you're parameterizing the 2s+1 polarizations in terms of the symmetric combination of these vectors, but the zetas as it is are only d-dimensional or 3+1 dimensional vectors.
Yeah.
Which in addition obey these null conditions. So
right.
You can't parameterize the most general 2s+1.
I agree with you. So this is just for writing down in general expression. So when I actually want to do some physical scattering with some physical polarization, I'll go back to this expression and I'll go back and forth using basically something like this. Yeah. So given let's say some function which you will see everything I'm writing in terms of zeta, I will just take a derivative like this to go back to this expression, and at this level I'll impose a physical polarization and all. This is just like a bookkeeping device to compactify in the expression. This doesn't have any physics. No.
But if you get a final answer, right? You have S factors of zeta.
Yes.
Then you just replace that zeta mu on to zeta mu s by zeta mu on. Right?
Yes.
That's a weak.
That way I can do. So you are saying given an expression which has this, I will replace by this, or vice versa.
Yeah. Okay. This is of course clear. Vice versa should also be unique, right?
Yes.
Because once you have the product of the otherwise there is zeta, there is a unique equal to.
Yes. And simplest way to just take the expression and just act like this, it will always uniquely give you this. So in that sense, this expression doesn't have any physics. It not even uniquely characterizes because this has 3 and it is null and all that. So it's just a way to come. Yeah. No. Yes, sorry. Thank you. So in this case, I should need a 1 over it. So this is the way I will use high spin polarizations, and I will only use this language. I will not keep this just because the expressions are big. Okay. So with that introduction to high spin polarizations, let's look at the state of the art and what is my motivation for this. So firstly, if we look at the perturbative quantum field theories with only massless particle has been well understood, I think. Then the next thing one can do is that the 3-point function of 2 massless and 1 massive, that has also been understood in last 3-4 years. Then one can ask is that given this 3-point function, what is the structure of 4-point massless scattering? So that's something we did few years ago, that to take this 3-point function and just trying to understand what will be the structure of 4-point function. So then the next interesting thing in my mind at least is to understand the structure of 2 massless, 2 massive amplitude. And any such amplitudes I will refer as Compton amplitude, even though the original Compton amplitude, the 2 massless were photon and the 2 massive were spin half particles. So this is the general terminology that I will be using. Now, this.
So what is the Emmy that 2 massive, 1 massive?
Yes, yes, I will talk about it. Yes. So, so the Compton scattering has been currently very useful to understand scattering of Kerr black holes. Especially given the Compton amplitude, you can actually construct one loop with it and you can derive various aspects of the PM expansion in that. And there has been a lot of work, especially started from Justin Vines and other people, a lot of works in this. So in that sense, this is something is already some part exists in the literature, especially, sorry, this is not me. Especially the expression of electromagnetic and gravitational Compton amplitude is also available in the literature using the massive spinor helicity variables. Okay, this is I think almost from 2018 available. But the main difficulty in that is that it's known for last 5-6 years that if you take opposite helicity for the massless particle, it is known to have spurious poles. It is known to have singularities which are not physical singularities. So in that sense, that understanding of spinor helicity variable is not a complete understanding. Not necessarily. So that's another motivation to understand it, because this is 4th dimension. But even in 4th dimension, let's say if you take a effective field theory perspective, 4D should be good for black hole. Why you go other dimension? Then massive spinor helicity should be able to do. But even then, the result is not complete. But also other dimension just for understanding. So now let me briefly go to the motivation, and at least there are 2 motivations that drives me. One motivation is this work by almost now 11 years ago by these 4 people that basically tried to hint towards, at least that is my understanding of that paper, that any higher derivative correction to gravity necessarily implies massive higher spin particle and vice versa. That's roughly, I think, the paper was trying to advocate, but it is not just sufficient to tell that, because you actually have to constrain the spectrum of high spin particle, constrain the 3-point function, and possibly one can do similar set of computation of time delay with a tower of high spin. So many things one can do as just a formal question, taking clue from that paper. And for that, one needs to understand the exact 4-point function of high spin particle. So this is one motive. Yes. So the reason they cannot do such, okay, so firstly in their paper, they took the string theory result and did this computation. I agree. So this paradigm is wholly based on the fact that you can talk about higher derivative correction without talking about loop correction. So that's, in my language, the mass of the higher spin is something, but not as high as the Planck scale. But one can take a more effective field theory perspective without really worrying about that ultraviolet question. And one question that one can ask is that what are the corrections of these loops due to massive high spin particle, let's say standard model. If there is a standard model coupling to high spin particles, how the beta function will change and all that. Will there be any observable signature? That's another effective field theory question one can ask. And another question that is, you will see that in recent time many people are using is doing this higher loop computation using higher spin to understand basically classical potential of black hole. So the way they're thinking is car black hole is like a higher spin particle, and they're trying to find the potential of two car black holes using this method. So in that way, they are also using a lot of loop computation. So that's basically an effective field theory way to ask the question. But they're not necessarily, right? Because the loop has something like this. So one would like to understand so this is a high spin propagator, this is a high spin propagator, and of course there are massless loops. So massive also goes into that. So in that sense, this structure of understanding this will be very useful. Actually, the way we came into this problem is very different. We were interested, as you know, that if I take a photon and couple it to some massive particle, pinhole particle in 3 dimension, then in the infrared, this loop correction due to massive particle gives you the Chern-Simons stuff. What we were interested that if it is not spin half particle, but if it's spin 3/2 particle, what is the Chern-Simons coefficient? And we could not make sense of, we cannot make sense of the question. We could not make sense of the answer. So that's why we came to this question, okay? Yes.
Yeah, this formalism itself, can it be used to understand, let's say, scattering of two black holes in the sense that in the sense of a merger?
No, I don't think merger phase cannot be treated perturbatively.
I see.
At least to the extent I have seen, merger has to be full numerical relativity. Non-linear things, yes.
I think what people do is that you use this kind of scattering to calculate the effective potential.
Yes.
Then you can use it for inspiral.
Yes.
Right? That's the reason why all these amplitudes
Yes.
people
Yes.
can.
But then I need a very good information of the potential up to very, very high order in spin
Yeah.
and everything.
Can you do that all the way? I mean, I guess that can be done all the way to the ring down, but can it be done for the output as well? Like, yeah.
Yeah. I have one question about this diagram.
Yes, this one.
So in string theory, for example, there are various kinds of hard spin particles, right? You can get from closed strings, open strings, leading Reggie, subleading Reggie, right? And they all have different amplitudes.
Correct.
So if you are going to use the scattering of higher spin to get something about curved black hole,
yes.
Okay, which one of those will you use?
So
Or
in 3+1,
Yeah.
there is only one type because it's only symmetric.
Okay, yeah.
So in that sense, I think 3+1.
Symmetric, but even then, this scattering amplitude, will it depend on only the fact that it's symmetric? Or there you can get closed string,
Okay.
you can get this can be a closed string state or an open string state, right?
So if I understand again, I think Orko Jyoti is here, he can correct me. The way they actually recover the black hole scattering is that they take mass goes to infinity, spin goes to infinity, keeping S by M fixed. And I think in that limit, all those subtle representation theory information, I have not proven it, goes away. Because it's not just quantum scattering they're interested. They will take it, write it in terms of some classical quantity and take that.
Okay.
But again, I'm not sure if other kind of particles will give some other result or not.
Yeah, I'm just wondering that these objects, so that they can have higher moments,
Yeah.
which the fact that the black holes don't have any tidal effect.
I'll come to the higher moment.
Yeah.
I'll show you in some time, and then we can talk about this.
Okay.
So
question is somehow whether the stringy particles know about it or whether there's something that you have to put in Excel.
yeah, I'll talk about it's encoded in the 3-point function. So when I talk about the 3-point function, will. So the main difficulty in this computation, I mean, it's basically a QFT1 computation. The main difficulty in this computation is the expression of the higher spin propagators is just humongous, and it just keeps on increasing as you increase the speed. Just a very difficult in general computational problem in general to do it on top of other things as well. Okay, so this is the expression of the propagator. Just wanted to show you I mean, there is no conceptual difficulty, at least in this expression, but it's just very, very difficult to compute this. I'll again come to that. What is the meaning of gauge? We have to talk about the gauge because.
But what you just showed, It's massive, yeah.
You're imposed all those whatever those.
No, no. So I think
That's what
so that the question is coming from the fact that it's a bit of going ahead, but it's basically what we found is that we postulated analog of Argyle gauge for higher spins. And that's why he's saying it's analog of some gauge. It's like, think like these are W bosons. So let's say take this expression and put for spin 1. Then this gives some W boson propagator. But this is a W boson propagator in xi equal to 0. So in that sense, he is saying it is some gauge. But xi in the gauge in the sense of taking a Lagrangian, fixing it and deriving it, I don't have an understanding yet.
I mean, it looks like there's a massless pole sitting.
Yeah,
right?
yeah. And that is there in xi equal to 0 because of the Woodby-Goldstone boson is massless.
Just unitarity and the fact that there's a pole, you know where the pole is, you know what the unitarity sums have to be. So just the on-shell, just the tree level, you might be.
It's not the on-shell, right? We also want the intermediate state can be off-shell in general.
Yeah, but if you want the tree level amplitude when all the 4 legs outside are on shell,
Correct.
and that's probably completely fixed by its behavior at what the pole says of
It's
the
completely-
intermediate, and at that point everything is on shell, including the intermediate part.
I agree with you. I mean, in the way we are doing, it's very similar, not very different from what you were saying. But the on-shell method that typically this spinor helicity people use using BCFW, that somehow gives rise to some sort of spurious singularities. So the approach we are taking is that let's write down a 3-point function, which I will going to do now. Then let's compute the 4-point function and check all the consistencies. Does it satisfy cutting rules? Does it satisfy gauge invariance? Is all of this clear? And then I go on and I ask the question, can I do 5-point function? Can I do 6-point function? But I do not do something like BCFW. I do just simple QFT, like just propagator 3-point gluing and asking questions.
Maybe the question about gauge I have not understood. So can you go back?
I think give me just 15 minutes.
How do you fix the propagator? Maybe that's the question, right?
Okay.
Yeah,
Okay.
Yeah.
So the propagator usually is fixed by the question. In the literature, the propagator is fixed by the question that, so these are symmetric, these are traceless. So you want something here which is symmetric in this news, symmetric in the news, traceless in news, traceless in news, and transverse. Yeah.
So that should be uniquely fixed.
Yes.
Right? So
Yes.
that's why
You don't necessarily transfer.
Yeah. Yeah.
Right. But I'm talking of, I mean, on-shell in the sense that, if you want to write a field theory, a Lagrangian, then you would want to anyway reduce the number of degrees of freedom.
That's why you don't impose del mu mu equal to 0 offset, right?
I mean, just to say in the gauge theory,
It depends on
mu, and that would also have been fine.
Correct.
You would not.
We'll see analog of that here also.
spin one particle, not thinking of some W boson, I mean, not arising from some mechanism. If I were to just write Procka-Lagrangian or something, then automatically like it is built into it that
But there is sort of
mu is.
But there, I think it's not the transverse offset. Inside. Because it's P mu, theta mu minus P mu over
M
square
square.
plus M, right?
Yes, it is not. It is not transverse offset.
So then if you contract with P mu.
Agreed. Yeah, even W boson propagator is not generally transverse offshell. It is only for xi equal to 0. It is transverse offshell.
This is the xi equal to 0.
Yeah. This is transverse offshell. This is transverse offshell. I think what the point you are trying to say is that why you are imposing transverse offshell, it should be just transverse onshell. That should be the minimum condition. Demanding transverse offshell is a too strong condition.
Xi equal to 0 is not a physical gauge.
It is a physical gauge for W. For Shannon model, you can do xi equal to 0.
That would not know, but I thought xi equal to 0 is when there is no oxidant.
Xi equal to infinity.
So xi equal to
That's where the would be go.
is my one.
Oh, okay. So my so my so my Goldstone propagator is this one.
Write the Weitman function because then it will be transverse off shell also.
But
you know,
but
in
in
the
the
case
white-
of the this thing you're writing down is the time ordered function.
Yes.
And then of course you get a delta function.
Yes.
But if you just write down the Weightman function, that really obeys the equations of motion. It just really literally obeys the equations of motion in both the variables.
But what about the question about this
Yeah.
tensor dependence?
Yeah,
How
so-
how the Weightman function?
Well, the Weightman function, you will be able to impose transversality at any p. It's just true that it'll be transverse. You know, if there's a
Okay.
because that's an equation of motion you impose, right? Which is
Okay. I
think that
didn't
p
try
mu
that.
times a mu is
You're
equal
saying
to
that. Okay.
derivative. So the Weightman function will just obey that. And then wasn't that an equation of motion for you?
One equation of motion is also transversality.
Depends on how you frame the Lagrangian, but yeah.
Yeah, but I thought
Yeah, so that's what, if you put it as a Lagrange multiplier, or it depends, I guess, on, then you will come back to this, you can put theta times del mu a mu, and then you get some. More general.
yeah, but right now there's no Lagrangian. So
No
say
Lagrangian.
we're just going to insist that the field, if you just look at the 1-point function, it satisfies d mu times whatever the field is.
Yeah.
Phi mu is equal to 0. That's correct, no?
Yes.
The 1-point function satisfies that. You will insist. You
I
wrote down
will
some
do that.
polarization vectors, right?
Yes,
Which were,
yes.
Then for the Weightman function, you can just literally demand
Okay,
that.
I'll try that. I have
And
not.
then and maybe that will give you I mean, once you have that, then you can get the time ordered one, of course. Just by
I have not tried. Let me try.
Again, the quadratic, I mean, when you say it's implicit, right? So
Yeah,
what
I
we
mean,
mean
he's
by
trying
the
to guess.
equation of motion.
I know, but he's trying to guess. So I was just saying that in this case, you could impose transversality off shell also. I mean, you just, I mean, there's no off shell. The whole thing will be actually concentrated on shell. You get delta function.
Yeah.
There won't be an off shell part to worry about it.
But I need the off-shell propagator because I want to construct that.
The time ordered function. Because
Okay.
the Weightman function has already.
Okay, you are saying this is the two Weightman function.
There's no notion of off shell for the Weightman.
Okay.
It just.
But-
is free function.
Yeah, but again, I think that's an implicit choice. There will be because I think that ambiguity will not go away.
So the ambiguity won't go away, but it will just be that then it will be clear what you are imposing and what you get. You will impose some conditions of the Weightman function, which
Yeah.
might be transversality, maybe transversality is the choice, and then you will just get
Okay.
the answer.
No, I think what Rajesh is saying that it will not uniquely fix, some ambiguity will there because that way the on-shell contribution, which is the imaginary part of the propagator, will be fixed. But the real part of the propagator will not be fixed in that way, I think. I'm not very sure because I've not done the computation. So
I think what we mean by on-shell will be the question. The Weightman function, if you impose that it's transverse, then I think that is the implicit choice of a Lagrangian or a.
That's fine. That's fine. But once you impose it, it will be unambiguously fixed. It will be only on shell. It doesn't have the off shell.
Then you could use the same thing to get the Green's
So-
function.
so
I mean the Feynman.
ambiguity is only there off shell. If you actually look at the residue at the pole, then all the things he is saying doesn't matter actually.
Then I believe there should be an ambiguity off shell because the Weightman function is given by the time ordered function, which is the off shell part, is given in it's a time ordered function, right?
Yes.
So you take the Weightman function, you
Okay.
put the right theta functions,
Okay.
it will give you the time ordered function.
Okay,
so
I'll
once
try that. I'll try that, but
There can't be an ambiguity. It must be fixed because once you fix the Weightman function, there is no more freedom. For what?
Yeah.
So you know what it is for p squared equal to m squared.
No, that's why I think the Weightman
Yeah.
function implicitly assumes a quadratic piece that it's. I mean, any Green's function assumes the
Yes.
equation
Yes.
of motion, the
Yes.
quadratic piece.
Yes.
So I think that's the question: whether at the level of the equations of motion you're imposing the k mu, the transversality condition or
Yeah.
not.
I suppose the point is, in the Weightman function also there's a gauge to be fixed also. That
Yeah,
is correct.
that's
because
what
the
I'm
Weightman
saying.
function not a gauge invariant object. But once you fix that gauge, then the off shell part is fixed.
so
Right. Right.
no. There is no gauge symmetry. There is no Higgs mechanism. I don't have any Higgs mechanism for spin 2. I don't have any Lagrangian to say there is a massless and it goes to massive and all that. So I don't have it.
Yeah, I mean, it's like in the Proctor-Lagrangian, how do you impose the transversality condition? If you want a Lagrangian that describes only the transverse degrees of freedom,
Yeah.
how do you do that?
So I'm sorry, I'm asking a basic question. The confusion is very basic. Now forget about the Lagrangian.
Yeah.
Just kinematically, you
Yeah.
have the field. You have
Yes.
to first tell me what the redundancy in description is. Before you tell me what the redundancy in description is, we can't say anything.
On shell there is no, off shell there is many.
No.
So let's look at the polar expression of the polarization.
Yeah, maybe yeah, you explained.
So the polarization on shell satisfies the condition it is transverse and traceless.
No, but what is the gauge symmetry here? You have to.
There is no gauge symmetry.
Then
There is no gauge. It's a massive particle.
See, the tension always arises whether you want to, while preserving Lorentz invariance, you want to write a Lagrangian which captures only the right number of degrees of freedom. So for normally a vector would have 4. If you have gauge invariance, then it becomes 2 for a massless one. But how do you make it 3? But the 3
Only on shell.
on shell. But if you want to write at the level of equations of motion or something, then the way you do it is you put a Lagrange multiplier xi times del mu a mu the whole square. And then you get this r psi like propagator.
Why are you so fixated on psi? R psi, because like you could have R psi around any other gauge condition, not Lorentz.
No. It's not a gauge condition. There's no gauge invariance. It's a projection. You're imposing, because you have 4 degrees of freedom for a vector, but you want to impose del mu a mu is 0.
But you could instead impose del mu a mu plus mu a mu equal.
No.
I think you are doing linearly.
Linearly. It's a free theory.
It's
Free theory at this point. And it's not a gauge symmetry in the sense that there is a gauge invariance. This is just a on-shell conditions which comes from the representation.
it projects out 1 degree of freedom.
There is no gauge symmetry.
But in the gauge that you have chosen, right? I think there will be many more auxiliary. This cannot be the.
Yeah. All your question is coming from, you are right. All your questions are coming from some Lagrangian or something.
No, I'm not string field theory. You can do this.
Yes, again.
But you have many more auxiliary.
I understand.
Yeah.
So what you will see, and hopefully I'll be able to convince you that firstly, we tried to do it using the Lagrangian. We could not do it. String field theory, I have not tried a lot. I have not tried much. You suggested me. Here in the on-shell way, we will reproduce all those results. And you will see that all the things you are expecting naturally from string theory to be true, we will see without writing down any action, just demanding unitarity and gauge invariance will give me those results. So that's the thing I want to present. There is no gauge invariance, there is no xi. All are taken some motivation from standard model, but just at the level of expressions, not conceptual agreements.
See, you have a lot of physical poles.
Yeah.
On this square poles. You have to get it. That's the except post like fields. You cancel those.
Yeah.
What is the problem with working with imposing the transversality?
Off shell.
Yeah.
Off shell, you will see what is the problem. Very soon I will show you
And the analog of xi equal to infinity gauge also has problem?
No. At tree level, it doesn't have problem. It doesn't have problem. Yes.
So that would be like eliminating all the auxiliaries.
Yes.
Just
Yes.
But how do you find analogs in xi?
We will talk about. Let me talk about 3-point and we'll go there quickly. So, okay, the question you asked. So the 3-point function. Okay, this result is known in 3+1 using spinor helicity, but this is true in any dimension. We can show that. So the number of structure is 2s plus 1 for spinors and 1 photon. Just for as a concrete example, I'm restricting to photon. So the question you asked, if it was scalar, there will be s plus 1 structures. And if it is graviton, then in high enough dimension, it's 3s plus 1. But in 4th dimension, some of them become related. It will become 2s plus 1. So these are basically the multiple moments. These are coupling to various multiple moments of the elementary particle. And one piece is very important. So let's look at this one and put n equal to 0. So that structure is like zeta 1 dot zeta 2 power s and epsilon 3 dot k12. So that is like the Coulombic interaction, which basically gives rise to the long range Coulomb force. Okay. So this n equal to 0 in the first line give me Coulomb interaction, and for purpose of this talk I will call it IR minimal coupling. Okay, and actually we'll see in this talk we will almost entirely focus on this interaction.
Sorry, why do you call it Coulomb interaction? I didn't.
Because if you compute the scattering amplitude and take the non-relativistic limit, that will give you the 1 over r between them.
So of this one.
Of this one with only n equal to z. Yes. So if you put s equal to 2, this should be massive graviton, but it has to be charged. So usually, typically, people take massive gravitons to be real, then it will not couple to photon.
It is not coupled to
Photon. Photon couples to only, yeah. I should have been, this should be one, I'm sorry, this should be only one. I wrote only the expression for photon. If it is scalar, then this doesn't survive. This is of course not there, and there is s plus 1. So scalar, you can also do a similar computation. Yes, yes, yes.
So there, n equal to 0 is the standard Coulomb because this is the lowest derivative term.
Lowest derivative.
One derivative coupling.
Correct.
And okay. And
but one derivative, you see, there is also one term here. The magnetic moment interaction from here is also same order in derivative, but it just because it has photon momenta, so that is long range, that is short range than Coulomb.
Yeah, yeah. So I'm saying in photon momentum, right?
Yes, that is the leading term. So that will give you the soft theorem.
This matches the Pauli theorem.
No Lagrangian. This is only the interaction. I did not write the kinetic term. I did not try that. Because the main problem, if I understand correctly in this literature, is that for arbitrary spin, nobody has able to write down an interacting Lagrangian with photon.
That's why I wanted to say scalars. Massive gravity is being investigated a lot.
Correct.
Yeah.
But I agree. For scalar, I think probably is possible. But as you will see in the talk, extra restriction and important restriction comes from the fact that there is a massless gauge invariance. I really want to use a massless gauge invariance to make extra things about the theory. So that will be very important for me.
But this massive graviton minimal coupling, that could agree with the Kaluza-Klein, right? If you do Kaluza-Klein of
yes.
Gravity to in,
yes,
right?
Yes, yes. But I think it will also comes with some magnetic moment. It becomes a magnetic moment g equal to 2. Because in gravity, it is automatically there from the angular momentum 3-point function.
Okay.
So in that sense, if you come from Kaluza-Klein, a very particular linear combination of them appears.
Okay.
Okay. So as I said, these are the 3-point functions which are related to the higher moments of the elementary particles. And this is related to what Ashok asked, that Weinberg argued that the natural value of the magnetic moment should be 2. And he had actually not a paper, he had a conference proceeding where he argued from UV behavior of the Compton amplitude generally. Okay. So in that context, one can in general ask that what is the natural value of the higher moment? Is there a concept of natural value of the higher moment? Is there a natural value of the quadrupole moment, octupole moment? We don't know, but it will be good to just get the results from string theory first and see what happens here. So as I said in this work, just for simplicity, I will restrict myself to the IR minimal 3-point function, which is giving you the Coulombic interaction. So this is the part which is will do the soft theorems. Yes. So here n equal to 1 will be, so this is like the dipole. So this will be the electric quadrupole and all that. Yeah. Great. So just I wanted to, before, even though I will not talk about it, this is something also a lot part of the literature is working on this. So in that sense, I wanted to, so these 3 people actually talked about another particular combination, which they also called a minimal 3-point function, but they called it minimal 3-point function from the consideration of UV behavior. Okay. So in their paper, they only restrict themselves to the 3-point functions, this 3-point function, and so they use massive spinohelicity variables, but let me take their concepts and convert it to using vectors and tensors. Then what it happens is that their 3-point function for spin 1 has this Young-Mills structure. Even though it is not Young-Mills in the sense these 2 particles are massive and this is massless, but the minimal they talk about is really a Young-Mills structure, which means it is coming from a Higgs metal. And then they postulate a similar 3-point function for spin S, which again has a Young-Mills structure, and then they have this extra piece.
Is the covariant derivative coupling or no?
In Young-Mills, it is a covariant derivative.
But in general?
In general, I don't have a covariant derivative. I don't have a Lagrangian matrix.
But there is no notion of minimal coupling in the general, which couples only to the charge and no magnetic moment or anything.
Yes, so that will be this one. That's the thing I am restricting myself. So that 3-point function is precisely this n equal to 0, this one.
Okay, and they are minimal.
They are not doing that. They are doing actually a particular linear combination of all of them which have this term.
I see.
There are 3 of them. You did some side. They have
So
cyclic thing.
for spin 1, okay, let me talk about it for spin 1. So for spin 1, what happens is that they take n equal to 0 from here, n equal to 0 from here with a very precise coefficient, which is g equal to 2.
And that gives you all the 3 terms.
That gives you all the 3 terms. And in this case, this is the structure they talk about. This part is probably not very obvious, but let me write it for you in our way. Again,
and this is a property of the Kerr black hole or no? No, not
that's
Kerr.
the statement that this is the 3-point function that comes from Kerr.
Kerr meaning Kerr Newman, presumably. Using
Yes,
the
I'm
charge,
doing
right?
electromagnetism. So there is an analog of this statement for gravity, and this will be in that case for
Oh, I
gravity.
see. I see.
Kerr Newman, I think also people showed the same.
Okay.
So let me just write this part for you in a more familiar way. So even though there is no gauge invariance for the massive particle, there is no gauge symmetry, anything, but nevertheless, I can construct something like a field strength, which is like this. A mu zeta mu. I can construct a field strength out of it, okay? It is analogous of Maxwell field strength, even though there is no gauge symmetry. Then this term they're talking about is precisely Z1 mu nu, Z2 mu nu, and this is raised. Okay, so in that sense, this is almost looks like there is some sort of a gauge invariance like W boson, something is underlying it, but it's not clear what is going on. It looks like a Higgs mechanism like structure, but not clear what is going on. So just wanted to tell you about this, but again, I will not talk more about this on this part. Yeah, yes. Yes, minus 1, and then this thing. Actually, in that paper, they also talk about for scalars, and for scalars, this part will be absent and this will be. So all the discussions can be also generalized to if the massless was scalar.
Right. If you would like to write any expression in terms of the on-shell polarizations of phi, you need powers to the S.
So you see, this also has exactly S. So this is S minus 1 and this has 1 power of zeta. Yes, please.
Since you want to think of that as the field strength, you're thinking of Xi as the some sort of a field gauge.
I would like to, but I still don't have a
Is
good.
there a sense of Xi propagators or zeta? Maybe?
No. I'm sorry. This you would okay. So you I'm very sorry. This is not a good way to. Where is it? Sorry. Oh. So let's take spin 2 for case. Just to show you the spin 2 case. So you can construct a field strength. Let's for this discussion call it Z, which has this thing Z mu nu rho sigma. So that will be like K mu K rho this nu sigma, and then mu nu antisymmetrized, and then rho sigma antisymmetric. Riemann tensor, analog of Riemann tensor, right? But now if you take this and write it in terms of zeta, then this simply becomes Z mu nu Z rho sigma. Okay, so in that sense, this is really like a field strength, like a Riemann you can construct out of it. It's just I'm writing in this short way. But what it means physically, I don't know. But that's a 3-point function they're talking about. Okay, fine. Okay, so let's now go to the Compton amplitude. So this is the Compton amplitude we're looking at. In my convention, which, in my convention, 1, 2 is massive, 3, 4 is massless, and this is just the Feynman diagram for T channel.
So you're saying just the previous slide, the one on with this. So this is what they got for
what they are calling UV minimal. And later the claim is that from the black hole multipole moment computation, this is also the 3-point function. To put it differently, if I take this 3-point function and take the large spin limit in the way they are asking us to take, I get the black hole multipole moment computation.
But this thing is not writable very easily in terms of these field strengths.
No. So the thing I am considering in this paper, actually, I think we can also do that, but I am considering n equal to 0, which cannot be written in terms of. It's like the minimal coupling of a photon to this.
It has no one.
It has no multiple moment. No.
All
my multiple moments are set to 0 by hand. Yes. Okay. So as I said, this is a bit of tedious computation, but it is doable. If you add these two things, you add the contribution from P and U channel, and you ask that question that whether the total contribution is gauge invariant or not. Okay. And if the way you check gauge invariance, you substitute pure gauge for the massless leg and you ask whether it is 0 or not, and the answer turns out to be 0. And as Ashok already said, that it turns out to be non-local because it has all sorts of 1 over p square poles. Okay. So what we do at this point, so I think, so I'll go back to that because I think the slides are not properly ordered. So what we do at this point, that we take some lesson from Higgs mechanics. And it is literally taking the lesson in terms of equations, not in terms of concepts, because I do not have a Lagrangian. So in case of Higgs mechanism, we know that a theory of charge massive spin 1 particle coupled to photon, the W boson propagator in the R psi gauge takes this expression. Now, moreover, very importantly, in that theory, there are these unphysical would-be Goldstone bosons which are important to ensure unitarity. Now, our situation resembles the situation of xi equal to 0 for spin, as Ashok was trying to point out. So then the obvious question we ask is that in case of xi equal to 0, as you know from W boson theories, that you cannot cure it, you do not get gauge invariance like this, you need to actually include these unphysical would-be Goldstone bosons to ensure unitarity. No, xi equal to 0, that is Ashok's. Xi equal to infinity.
This is the propagator with 1 by 2 xi squared, right? And then
No, I think that xi is in the Newman.
So xi is here.
But xi equal to infinity.
In xi equal to infinity. Yes. So then the would-be Goldstone boson becomes infinitely massive. So there is no would-be Goldstone boson, it's only the p mu over m square, which is the Procol-Lagrangian tells. So our situation resembles xi equal to 0. So at that time we tried many things and we said, okay, let's see what happens. So let's take this lesson literally, and we took the question that is there an analog of R psi gauge for high particles? And then the obvious question is that can we restore unitarity by adding extra particles? All at the level of scattering amplitudes, no Lagrangian. So then what we did is that in that high spin propagator, we ad hocly take all those projectors and we replace it by this expression. Okay? And what we find from our computation is that there is no way, I mean, we tried to add all possible things and everything, and you cannot find a solution apart from these 2 points of xi, which is xi equal to 1 and xi equal to infinity. In particular, the original problem of xi equal to 0 does not work. It does not have any solution. You cannot add anything to make it gauge invariant. No contact term, no exchange, nothing. It has no solution. So in that sense, the gauge comes back here, and as if there is a massive, some sort of a gauge invariant. But again, this is only at the level of, no, this is for the massive particle. This R xi, this xi comes from really the W boson gauge. Sorry? Yeah, photon propagator I'm gauge invariance I'm checking. But in order to do that, I have to, I mean, firstly, the original problem, which is off-shell projector, is not good. Yes, correct. And what it seemed to suggest, just in terms of just analogy, not still a proof, that there is also some sort of a gauge invariance for the massive legs. That's what that's why I discussed with you the other 3-point function more elaborately, because this 3-point function which these people are talking about also has some sort of like a field strength like structure for the massive leg, which has no reason to construct any field strength for the massive leg, but that's the 3-point function they're talking.
We are both for xi equal to 0 and infinity. There are no unphysical poles, is that right? There may be double multiple poles.
For xi equal to 0, there are
not 0, xi equal to 1 and infinity.
Xi equal to 1 and infinity, there is no unphysical.
All the poles are at p square equal to minus m.
All the poles are p square equal to m square. Correct. Yes.
And you know if they are equivalent or you don't know?
That's I'm coming.
Okay.
So let's first go to the simple case when xi equal to infinity. So in case of Higgs theory, we know that in case of spin 1 particles at xi equal to infinity, the unphysical would be boson and become infinitely massive and decouples. So only a contact term is enough to ensure gauge invariance. We found the same thing, that one can only find a local contact term to restore gauge invariance for any spin. Okay, and this is the contact term for the photon. I can restore gauge invariance just by adding this kind of a contact. Oh yeah, sorry. The reason I skipped it, this expression. So this is roughly the expression looks like xi equal to infinity. This is the expression after the poles. The T-channel expression looks something like this. And if you put epsilon 3 equal to K3 or epsilon 4 equal to K4, this expression is not gauge invariant. It's not gauge invariant after two poles added, but the gauge invariance can be restored by adding these contact terms. And very importantly, you see, this is the kind of contact term we get in scalar QED. And these are the extra contact terms which you appropriately see in standard model Lagrangian is also present. Of course, standard model is not just the minimal, it has the multipoles, but this thing is present. We checked also the standard model works in this way.
Because in the xi equal to 1 case, you have multiple poles?
No, I have only one pole.
But multiple powers in the numerator look like?
No, for xi equal to 1.
Let's say xi equal to 1.
Yeah. Yeah, so xi, oh, I'm sorry. Yeah, so this is the expression of thetas, and it has poles like this. But xi equal to 1, you will see this term drops out. Only eta mu nu remains. Theta becomes eta.
1 minus xi. That's a Feynman.
Yes, that's a Feynman gate. In Feynman gate, sorry, Godwin. Yeah, you will see. It will come back. It will come back. Okay, so this is the thing. Okay, sorry.
Yeah, I think the language of string field theory, I think this xi equal to 1 is not a single gate. And
yeah.
When you eliminate all the auxiliary fields, that will be like xi.
Yeah. So we'll yeah. So so this is a simple thing. So you see that you take this, you in this Compton. Okay, let me not go there. So in Compton, you add these two exchange diagrams. If you take this contribution, so there are these massless polarizations. You replace the polarization by the pure gauge polarization, and you ask the question whether scattering amplitude vanish or not. What identity? Yes. Okay. Sorry. Yes. Electromagnetism, which we expect, and it does not unless you add the contact term. Okay. So this is the contact term. So in that sense, xi equal to 1 is infinity is very clean and very nice, but I wanted to see other points if it is possible. And partly because we know that in standard model, there is no way to prove renormalizability for xi equal to infinity. So at least some other point will be good if there is any make sense of gauge invariance and all. So then we look at the expression for xi equal to 1, where the T-channel expression just simplifies a lot, just because the projector simplifies a lot.
But what would you do if you had just scalar then, massless scalar instead?
Then there is no gauge invariance.
Yeah.
So that's what I was telling Rajesh, that for massless scalar, I will stop at the level of computing this amplitude. I do not have this gauge invariance to dictate me anymore.
Okay, but then there is an ambiguity in that case.
So that's the reason I like this, because it helps me to figure out the propagator and all this thing in much better way from massless or IR perspective, that what is the IR thing. There is a way, there are 1 over p square poles. So what is the residue at that pole and what is the meaning is one question you can ask. But that's we did not try it much.
Once you have chosen a propagator, the same propagator has to be used for everything, right? So you have to have consistency for electromagnetism, gravity. If any of them fail, then the propagator is not good, right? But gravity you cannot not know about, right? So these presumably can be done with gravity also.
We have done it. Okay. Yes, I'll talk about it.
Yeah.
So this case, the expression simplifies.
So why are you bothered about renormalizability? I mean,
not really. I mean,
it says xi equal to infinity.
No. Okay. So as I said, firstly, for EFT perspective, I want to do loop computation, and also for two reasons. If I want to couple it to standard model, or I want to couple it to, let's say, just in the black hole literature. Okay. But let's say we don't at all cared about, we are only tree level. Then even in tree level, I wanted to know that for spin 1, all values of xi work in standard model. In standard model, I can show it xi independent. Here, is there only one point in xi that gives me nice answer, or there is any other point? And
there's nothing as such wrong with the xi equal to infinity.
No,
answer.
not at this point. Not at this. So yeah, I mean, it's just my own mental bias. I want to only show xi equal to 1 is good, xi equal to infinity is not. But that's my hidden bias. Okay, so this is very simple expression. It very thing.
But I don't know, in string field theory also you can probably add some arc kind of thing. Right? Why not?
That's why I have to check that computation, and I want to do that, and then I can see what it means for this.
Yeah, I mean,
yeah,
you can always break gauge inference by adding some gauge fixing term, right?
Okay. No, I don't know that part. So yeah, maybe something can be done. So here you will see something like Siegel gauge. So in this.
Exactly. Yeah.
Yeah.
Xi equal to infinity. Yeah, I agree.
It's very.
But I'm saying that in principle, I mean, in string field theory, the quadratic Lagrangian is quite well. There's a confusion there, right? And you can treat this as a normal gauge theory, which has gauge invariance, and you can add gauge fixing terms. Yeah. So there should be another of arc psi gauge also.
Yeah.
Why aren't you doing what he's saying, string field? Why are you doing all this?
He doesn't like string field.
So yeah.
No, it's much simpler than this, I'm sure. He said you have to calculate a quadratic term, right? Phi q phi. How difficult can it be?
No. Your question is very valid, and I was telling Rahul that before we come next time, we should have the string field theory answer. So yeah.
String theory computation of some massive particles, and you could ask, so are these matching with that? Just the
we have not done that yet. It's not.
You'll not put a propagate. You'll just write down the final answer. But the final answer you can check if it matches with. That's not that hard. Actually, if you do 4 point, it's not impossible.
It's not very hard. We just we have not done it. See, point is that it is not very hard to get a string theory answer, but we really have to focus on that level. And we have to make sure in that level there is only one massive particle, no other massive particle. Those details could be.
Where was that important? There is only one.
Because here I'm only doing for one massive particle. Right? Here I'm only using one massive high spin particle. But in string theory, apart from first few level, there are multiple physical particles at every level. So those details can become a bit more, work. That's all. I cannot just literally match. I have to, because string theory, then I have to take the full spectrum and understand it in this way.
I mean, the problem is that if you're going to claim in the end that there's a way one can get an answer for this 4-point scattering, then it has to account for all these other possibilities, right? There might be additional particles being exchanged. There might be lots of other stuff happening. So maybe some of the constraints you're putting, saying that you only can, impose this or that might be relaxed if you had additional particles.
No, see, the only condition I have put till now is massless gauge invariance and unitarity. Those two conditions cannot be relaxed.
Massless gauge invariance, is it clear that only one kind of, maybe that's also only one kind of diagram can contribute? Then that should also be true in string theory. I mean, all I'm saying is that, if, so you drew one diagram which I guess had the massive line going through, or?
So this is for photon.
Yeah.
So this one you are saying.
Good, excellent. So
there are two diagrams. I only
Right.
drawn one. Yeah.
Right. So then you don't care about if there are other massive particles, right? How does
No,
it
but
matter?
in
You
the
put-
exchange, there will be all the massive.
No, because you put like the two massive particles on the IC, on the external legs, and you're saying some other thing could be exchanged.
Everything will be external. So I have to focus on that level and then actually make sure even in that level, only that particle survives. That I'm not saying it's hard. It just we have to do it a bit more carefully.
Well, yeah, I think string filter, what you can do, the things which are not in that level, those you can eliminate out.
Easily, yeah, that will be easier problem. But that level we have to put a projector.
That level that we want to.
But so far not considering a massive photon
Massive photon, no. No, that will not cure this problem. Because the massive photon vertex is only through the field strength of the photon. That classification has been done by Siraz and company, and that cannot cure this gauge invariance. Yes. Actually, you can do all this. Can a massless gauge invariance cure it? No. Can any other mass exchange cure it? No.
Other mass. You're saying that other mass exchanges will interfere or they won't be?
They will interfere as a physical particle. But are they necessary to get massless gauge invariance? The answer is no. But string theory doesn't just have massless gauge invariance, it also has this massive gauge invariances, which I still don't understand very properly. Without that, I can just talk about one massive particle, no problem. Okay, so so this is the point Ashok was asking. So this satisfies gauge invariance by this, but point is that it doesn't satisfy cutting rule. If you take this diagram, look at its cut and ask the question that in the cut, all the physical degrees of freedom of the massive particle contributing or not, the answer is no. So this answer is not unitary. But again, as we know from W bosons, apart from contact term, we can add particles ranging from spin s-1 to 0 to ensure unitary. So we can add a range of particle in this case. They come with a very precise 3-point function, which is dictated by the original 3-point function I started with. And as Ashok has been, this is very similar to the feature of xi equal to 1, where the unphysical particle and the physical particle have the same mass. So this is what we get out of this computation. But this is the question I still have not managed to answer. We have not managed to answer that. Are these something like the would-be Goldstone bosons? Is there a Higgs mechanism for massive high? Okay, so one goal could be to first prove the Goldstone boson equivalence theorem here and then to go ahead with this question. But the reason we have not done it, I'll come to that point very, very quickly. So now another question I think is that, can you prove it xi independent like spin?
You could do this.
Yes.
You can, I mean, you have found these vertices.
Yes.
With the particles.
Yes. Yes, and it's uniquely fixed. All the vertices has to be very precise number, very precise everything. So any other xi, will it work? Because at least for spin 1 it works. We have proven that it cannot work for any other xi. So only these two xis work. That's a proof we have.
By adding only these terms.
Yes, and asking for a solution which the 3-point function is a real number, not function of Mandelstam variable. So if you add the 3-point function, the only ambiguity is that the coefficient should be something, but the something should be a real number, not some function of Mandelstam variable. With that condition, we can show that there is no solution apart from this two.
But that's assuming that very specific structure.
No. Yes, this structure. Correct. Correct. I only use the same structure of the property. Correct.
Yeah, the fact that specifically those product of theta, right?
Correct.
What I was suggesting, if you take the gauge invariance in filter Lagrangian and add a gauge fixing term, you will not keep things in that structure.
Agreed. I only keep that structure and just tweaked it with xi. I agree with.
Yeah, exactly. That's right.
Sorry, to understand the previous statement, if you want to consistently describe spin S with a gauge field, the photon, You have to add all the lower spins, you're saying.
At this point, xi equal to, if you use that propagator.
Yeah. Assuming that the propagator for the spin S is what you're saying at xi equal 1.
Yes.
You have to add consistency, you have to add all the lower spins with the same form of the propagator.
With the same, with that propagator and with a very precise 3-point function, I have not written, but I can show you a very precise 3-point function.
So coefficients are fixed and all propagators are fixed.
Yes.
All the way.
Propagator is not fixed. Propagator is more like our postulate. We started with a form of a propagator.
Yeah. This is for all spinners.
Yes.
Yeah.
Yes. All bosonic spinners we can do this. QCD, but QCD is yes. Okay. So the xi independence we could not show, but I'm still hopeful for the following reason. As I told you at the beginning of the talk, that I only focused at a particular 3-point function.
Do you get the same answer as like the Bosonic?
Yes. Because the answer has to be matched because of unitarity. Cutting rule says these two answer has to be same.
Contact terms out.
Yeah. Contact term, but the unitarity says the residue. The residue matching says that. So of course, with this I can always add a genuine 4-point contact gauge invariant term. 2 photon, 2 massive. There are genuine gauge invariant 4-point contact term. Those ambiguities I'm not resolved. But I'm hopeful. Yes, because of gauge invariance. If it is not gauge invariant, then anything cutting rule you cannot talk about.
That is unique for
Yeah, I mean, the contact terms are not identically same, right? They're not identically same, the contact term changes. But it changes in a way that the final answer is same and it satisfies the cutting rules. Correct. That's what we found, yes.
For other psi, you're saying you can't even add the contact terms.
No, because there are poles. First I have to cancel the poles.
Yeah, no, suppose, but you said if you cancel the poles, you don't get something gauge invariant.
No.
But can you add something, a non-gauge invariant contact term, which would cancel that?
No, for other xi, we did not find any exchange or any 4-point contact term to resolve the problem. We tried both.
At least the sum of them.
Yeah.
Individually they don't, but the sum also.
No, for spin 2, we put the most general thing and tried to solve. We could not. Maybe we should put that part also. So
if you have tried to get this by on-shell method, presumably you'll find the same answer, right?
That's what I was telling you. If I don't understand spinor helicity very well, but okay. So in order to do that, I think the spinor helicity people mostly use BCFW. And in BCFW, I don't know very well, but I think there is a problem with the contact term at infinity. Not everything is BCFW reconstructible.
Yeah, I agree.
So if I understand correctly, that for higher spin, that contact term at infinity, the local term at infinity at BCFW has not been properly resolved. Okay, so in that sense, I could not match. But the second reason I could not match is that these people, all these massive spinor helicity people are all focusing on this other 3-point function that Niemann people are talking about. Whereas I focused on the opposite extreme of the 3-point function, which is the soft theorem 3-point. We could not find any result of this. So there are, so the black holes have a very different 3-point function. Their 3-point function is a very precise linear combination of all the multiple moments. Whereas the 3-point function I am focusing on is all other multiples are set to 0, only the coupling to the charge is remaining. They are focused in that for the reason that it apparently reproduces Carr black hole. So I understand why, but that's why they are not focusing on this. However, I am hopeful that it can be possible to show xi independence for the following reason, that as I said you, that I at this point only considered a particular 3-point function. I still have not considered all the 3-point functions. So then there is this 2s plus 1 3-point function. Then maybe for some special points in that 2s plus 1 dimensional space, maybe we will find a solution. I don't know. So that part we have not resolved. But as I said you, that a few extensions we tried to include gluon. It works. This method works. Till now we have checked it for lower spins with graviton. Again it works. We checked that whether this result can be reproduced using the massive spinor helicity formalism without referring to any of this literature. That also works. but that's the result we derived first time. The other literature do not exist. So this is like using massive spinor helicity, this kind of things. So as I said you already, that the open question that remains at this point, and I think that's probably in my mind, the most important would be that, is there a Goldstone boson equivalence theorem? How to do that? This part, I think now we have a bit of an answer, but we have not cleaned it. That in this talk, I only focused on a particular 3-point function, but maybe that particular 3-point function, at least in any physical theory, at least the magnetic moment coupling is present, right? So maybe this truncation is not a physical theory. So what about doing the most general 3-point function? And is there a special point where the UV behavior of the amplitude becomes better? Okay.
Don't you fix the external polarizations to something and then restrict to a class of 3-point functions?
No,
Because
my 3-point
others-
function was ad hocly chosen to be the minimal, not
The Coulomb one.
Yes.
Yeah, but
not because of external polarization.
no, but I'm saying the other ones may not contribute to a given process.
For a given process may not, but there are processes where it will contribute.
Yeah, but if all you are caring about right now is to check whether the answers are Xi independent.
Okay.
You can ask for any given process.
I understood your question. Let me say it in this way. I do not know a process where only the Coulomb contributes and nothing else contributes. So I can say this is a conclusive proof.
I see.
Okay. And yeah, this is what hopefully when I come next time, I'll have an answer to this question. So can one write down an action for this? Yeah, I end here.
So if I just take bosonic string theory, since you're doing tree-level calculations, so I know I can write down the vertex operators for these objects, and I can compute the 4-point function. Maybe it's difficult, but in principle possible, no?
Yes, it is not very difficult.
So then you have an answer there, right?
I have an answer, but not for this, because the string theory 3-point function is again all the multiple moments with very precise coefficients. So let me go back there. Yeah. So string theory, all these 2s plus 1 are present. For bosonic string theory, I checked it. All 2s plus 1 is present with a very precise coefficient. So what I am doing, which is again, I'm just truncating to the Coulomb because it's soft theorem. I cannot just get that from string theory.
But in the limit, when you take the external photon momentum to 0, then you should get back that.
I agree with you.
String theory result and go to the soft limit, right?
Soft theorem should work.
No, soft theorem of course will work. But I'm just saying that if you just take the external photon momentum to be small, then shouldn't the other contributions go away?
Yes.
Yeah,
there are more derivatives. Yes. There will more derivative. Yes. Correct. Yeah. It will go away. Yes.
So can't we extract the actual answer that you want by taking some limit of string theory results?
Yeah, but as you see, then first I have to truncate to that level, then remove the other states, and then I have to do this. So it's possible, but we have not really put a lot of 3-point function. I have done it. I saw that very, very, very precise coefficients comes in that way. As you said, it's not difficult.
Like the magnetic moment and the electric moment thing comes together in some sense.
Yeah.
But not in the soft limit.
Yeah, but soft limit is the extreme limit. But what he's doing is, wouldn't there be, I mean, can you consistently truncate beyond the soft limit?
Because they're same order in momentum.
Because I wasn't sure that what he was doing was really a derivative expansion in the string sense.
No. Because in the same derivative order, the magnetic moment contributes.
Okay.
Yes.
So,
yes, correct. It's only suppressed in the soft limit of the photon moment. Otherwise, it's the same order in derivative.
Yeah.
Right. Yeah. So in that sense, having the general result. So that's my. If you ask me, my plan is to first derive the general result from here, and then put the string theory value and compare the full string theory result with the general. Otherwise, this will be very difficult. I still don't know that, but the way I will say I will have a good theory is hopefully having a proof that any tree level endpoint scattering and one lobe scattering is good. But I am very far from this.
It's unitary.
Unitary, yes. Renormalizable, unitary. There is proper rules to construct it. If I have it, then I will say that, yes.
Because inside equal to 1 and equal to infinity, and then perhaps max them.
I knew, so we were trying that last night. Hopefully before leaving, I'll give you an answer to that. Yes, so let me tell you, for spin 1, we checked. For xi equal to 1 and infinity, we checked, it works. It gives the transverse photon propagator. But one is we have a good quantum field theory. So if we do spin 2 and we get the same result, then I will tell you, okay, we have a result.
So what that diagram?
Yeah, that diagram in 4th dimension.
No, I thought you were talking about this diagram.
Oh, this will be much harder. We first tried with this and show that the photon propagator is this k nu minus eta mu nu k square. That is at least coming transverse. This we checked. So my plan is that if we get the photon propagator transverse, then we'll go to 3 point and then go to 4 point.
I think that's bothering me. If you just take, for instance, massive gravity and you couple it to a photon in this way, you don't expect that by itself will give you such a simple, such a simple theory which will be unitary, right? You know that shouldn't work.
Yeah,
like
but
you've just fixed the 3-point functions and the propagator, and you know that shouldn't be enough to give you a unitary.
Yeah, your statement is
unitary. Well, tree unitarity, maybe if you just take these 2 external particles, it's not even clear to me if you take arbitrary number of external particles at tree unitarity.
I agree.
It won't
arbitrary with that's what I spelled to Spenta, that this is just a starting point. I have to first have a proof that all endpoints are consistent.
Actually, I'm also a little confused why you don't need the 4-point contact to just, let's say you put 4 external of these massive guys.
Yes.
Then again, you will need some 4-point contact, right? You should also check unitarity for that, not just for 2 massive 2 photons.
So you are asking me about this plot, right?
Yeah,
so,
and that should not be easy to figure out. No. Just 3 level.
2 massive, 2 massive.
No, 2 massive, 2 massive. I was thinking 2 massive to 2 massive. Yeah, I was thinking of all 4 massive.
This one you were asking.
No, I was thinking just contact diagram. You want to just a contact diagram all 4 massive. Yeah. So that should also have it should be somehow required, right? Like we know in the case of gravity, the 4-point contact diagram is required by gauge invariance.
So I understand. So the point you are saying, I know there is a proof of this. So you can ask.
Yes. Yeah. This process.
This is okay, but if you want to construct a theory, you have to
that how would you reproduce the Lagrangian results? That's I think what he's asking.
My question.
Yeah.
My question not that there's no. Let's say you don't have a Lagrangian. You just want to write down amplitudes. But all these should somehow be required.
Yeah, I understand your question. So let me tell you how I will go ahead and figure it out. So the point is actually showed in one of the paper by Satish Joglikar, this matrix derivation of Weinberg model. So there he shows how you can figure out 4 massive contact terms by demanding that how the scattering amplitude is growing in the ultraviolet and demanding certain particular growth in the ultraviolet. So basically this A square kind of growth people talk about. If you put that kind of restriction, then that will relate the 4-point contact coefficient with this kind of condition. I have not still used any of those conditions from UV. I only used IR conditions. So I think there is a way by demanding UV behavior, but we have not still focused it. We only focused in the IR behavior and first curing it, then going to the UV behavior.
Massless, of course. There, I think it's not a UV thing. It's true that root minus GR.
Massless gravity.
I was not asking. I was asking on massive. But I was saying in the case of massless, the 4-point function will be fixed in terms of the 3-point function.
Unitarity.
Just but yeah, unitarity demanding you have only 2. So are you saying in the case of massive that relation just goes away? There's no 4-point contact that you have to impose?
Not by gauge invariance kind of unitarity.
You had a 4-point function in xi equal to 1 gauge.
Yes.
Photons and 2.
So yeah, so this kind of thing I can figure out by massless gauge invariance. But this kind of thing, I do not have any gauge invariance to begin with. This I can figure out by demanding that exchange plus this is some nice in the ultraviolet, and that will relate this.
Yeah, I was actually worried because these people, Claudia de Ram and so on, they spent a lot of time trying to figure out these interacting theories of massive gravity. Now, there the graviton is not charged as you have here, but that seems to be a pretty intricate thing. It's not just easy to write down one of these things. So it seems like a constrained structure, and I'm somehow missing where the constraints will come here.
Demanding nice results for these open functions will involve extra restrictions on.
Yeah, I think this, demanding nice results for many other properties that you would want, other scattering amplitudes, I think will put a lot of conditions. Like just asking for this two spin s, 2 photon amplitude might be far from sufficient.
Agreed, absolutely. This is, as I said, the way I'm looking at it is to first make all massless consistent, then look at 2 massless, 2 massive consistent, and then to go for 4 massive consistent, and then to go for endpoint function, or to do string field theory. So what you are asking is, I just don't have an answer, but this is something I will do once I clean up all the Compton scattering.
If there are no other questions, let's
Consistent theory of massive spin-one particles.
I think this paper by Joglekar also tries to prove this. I mean, there are other papers also, but this is the paper I understand the best. Yeah, so, and that's all the rules of standard model you can derive just from this consideration without write down a all 4-point functions, everything. Any suggestions apart from what you already gave?
The first thing that occurred to me was the consistent theory of higher spin fields is.
No, but Spender, that's what I was trying to tell, that I wanted to prove it that from asymmetric way that you should. So in that sense, I'm coming to from the other perspective that
string theory also came from asymmetric theory.
Yeah.
Okay. No, I understand. Very difficult.